All right, everybody. Thanks so much for joining us. We're super excited to have you. Welcome to SAS Innovate. Whoo, yeah. Let's start the cheer. Are you guys excited to be here? We're excited to have you. Today we've got an amazing presentation from our friend over here, Michael Lamb, to talk to you a little bit about causal inferencing. He's an expert in everything econometrics and everything statistics, and he'll be able to talk to you a little bit about what we've been doing with this program. Without further ado, Michael, take it away.
Thank you very much, and welcome to SAS Innovate 2025. My name is Michael Lamb. I work in the statistics group at SAS, where I manage the advanced regression team. And it's my pleasure to be giving this demo today on flexible predictive modeling with PROC BART, with a particular emphasis on applications to causal inference. As an outline for this demo, we'll begin with a kind of brief introduction to Bayesian additive regression tree, or BART models, cover a little bit of what these are and how they compare to some related techniques. We'll then discuss the connections between counterfactual predictions and causal inference and what makes BART models kind of so well suited for this task. And then we'll look at some examples demonstrating how you can perform these types of analyses using the BART procedure. So kind of jumping right into things, from a statistical perspective, you can think of a BART model as using a sum of trees ensemble to approximate the conditional mean of some response variable for the purposes of prediction. So by using a sum of trees ensemble, BART models are going to be non-parametric, meaning for this mean function f of x we're approximating, it can be any mix of continuous and categorical predictors, and we're making no assumptions about what type of interactions or nonlinear relationships there might be between these predictors. It can be arbitrarily complex. You don't have to pre-specify it. Now, an attribute of BART models that is unique compared to other tree-based methods is that the BART model isn't going to give you just one estimate for this ensemble. Instead, the fitted BART model is going to consist of many posterior samples of this ensemble produced by using this kind of very clever Bayesian backfitting MC-MC algorithm, where a form of Gibbs sampling is going to be used to take a current sample of the ensemble, sequentially modify each one of the individual trees in it, and produce your new posterior sample. So the way you would get predictions from these BART models is by evaluating each one of those saved samples of the ensemble and then averaging across all of those to get your overall model prediction. And if you've saved a sufficiently large number of posterior samples, then you can very naturally take this Bayesian approach to uncertainty quantification by assessing variability across the predictions from the posterior samples. Maybe check the guy in the back. Say by computing Bayesian credible intervals. So that is our introduction to BART models at this high level. I now want to talk about them a little bit more in the context of other tree-based ensembles. So maybe two of the most popular sum of trees ensembles models you might be familiar with already are gradient boosting and random forest models. Now, in the case of these algorithms, trees that get added to the ensemble are grown individually in a greedy fashion. So to try to limit overfitting to your training data and get a model that generalizes well in terms of predictions, some forms of regularization have to be applied to limit that overfitting to the training data. And for these algorithms, that typically takes the form of some hard constraints on the individual trees, like the maximum depth that they can be grown to, right? Now, setting these types of hard constraints can be a little bit challenging, since if you make them too restrictive, your model may not be able to be complex enough to capture all of those potential interactions that we said you don't have to pre-specify and may be there in your data. But if you leave those constraints too loose, then again, you end up with a model that overfits to the training data and doesn't perform well in terms of predictive performance as it generalizes. So typically for these types of algorithms, to get the kind of top of the line predictive performance, some form of hyperparameter tuning is going to be required to set those parameters. In contrast, as I mentioned earlier, fitting a BART model uses this Gibbs sampling, where we take our current sample of the ensemble and produce a new one by sequentially sampling updates to each one of the individual trees. So in the case of this BART algorithm, we're not growing trees individually in that type of greedy fashion. And the way in which we'll be applying regularization to get a model that generalizes well in terms of predictions is through the prior that we're using to guide this sampling process. So a unique feature of this kind of approach compared to these other algorithms is that, kind of again, classic Bayesian fashion, we're not imposing any hard constraints on our model through this prior, right? It's some soft constraints representing our initial beliefs, but of course, during our sampling process, that's going to get updated and adjusted based upon the data that we're analyzing. So for example, while the BART prior places greater prior probability on really simple individual tree structures, again, this isn't a hard constraint like you have in those other algorithms. And it's not uncommon to end up with very complex deep trees in some cases, since the probability of accepting the operation of splitting a node in an individual tree is going to have a high probability of being accepted, even if it's very deep, if there's a great improvement in the fit towards the data, right? So that's something very unique to BART models. So if you want to contrast BART models with other tree-based methods, at a high level, you can think of these BART models as being produced with this kind of stochastic random search of your model space, where that's being guided by that prior that's again applying regularization, but also, of course, the fit to your observed data. And again, this can be contrasted with that greedy approach used for gradient boosting in random forest models, where typically some hard constraints and hyperparameter tuning are going to be required. Now, another way in which BART models are going to differ from other sum of trees ensembles, also tied to the Bayesian attributes, is related to the size of these BART models. So for your gradient boosting in random forest algorithms, you may end up with an ensemble of a few hundred trees, typically. For these BART models, the default model is going to consist of 1,000 samples of a 200 tree ensemble. So in total, 200,000 trees, right? So this is going to have some implications not just for how long it takes to train these models, but it'll also have some implications on how long it takes to score new data using these models, since doing so is going to require, again, evaluating each one of those safe samples, so routing that observation through, by default, 200,000 trees. Now, there are some benefits, though, that come along with the size of these models. One of which I mentioned earlier is, again, by saving all of those posterior samples of the ensemble, we can very naturally take this Bayesian approach to uncertainty quantification by assessing the variability of the predictions from all those samples. Again, think computing Bayesian credible intervals. Another benefit is that in practice, it's been observed that the fit of the default BART model without any hyperparameter tuning tends to be competitive to other sum of trees methods when implemented with hyperparameter tuning. And on top of that, the predictive performance of these BART models tends to be robust to any type of reasonable changes in these prior parameters, right? So that's going to kind of make it so that these BART models are very easy to specify and train, right? We just need to specify our response, our predictors, which of those are categorical, and we can kind of ignore all of those other hyperparameters in the background. You can think the tuning of those parameters is already kind of baked into that stochastic search algorithm that's being used for producing all of these samples. So to summarize, while some attributes of BART models are going to make them ill-suited for the analysis of truly big data, think millions, tens of millions of observations or more, those same attributes are going to make BART models really well-suited for the analysis of small to medium-sized data sets, think hundreds, thousands, tens of thousands, maybe a few 100,000 observations. And especially so in situations where your data might be quite noisy. The stochastic search algorithm does really well with that. And also in cases where there may be a good deal of uncertainty about how the predictors are related, and also in situations where uncertainty quantification is going to be a priority. Again, something we can very naturally do from this Bayesian perspective, harder to do with those other algorithms. So that's our overview of BART models. Let's talk now a little bit more about counterfactual predictions and their connection to causal inference. So when reasoning about causal effects and thinking about defining them and what's necessary for their estimation, a potential outcomes framework is very commonly used. Now, this is something I have taught anywhere from 2-hour to full-day continuing education courses on at professional development conferences. So no, we're not going to be getting into all the nitty-gritty details of the causal assumptions that allow us to give causal interpretations to these quantities. But at a high level, you can think of these potential outcomes as being a really powerful tool for formalizing what-if type causal comparisons. So to that end, if you're interested in studying the effect of what we'll call a treatment T on an outcome Y, Within this framework, you would begin by imagining there exists for each observation these potential outcomes defined for each level of the treatment that correspond to what the outcome for that observation would be if they were assigned that level of treatment. So with these potential outcomes, it's very natural to define a total individual level effect of, say, receiving treatment T1 versus T0 by just looking at the difference between those potential outcomes. So this individual level effect is something we typically can't estimate reliably, but it gives us a starting off point for defining these different causal estimands, like the average treatment effect, the expected value of that difference, or the average treatment effect for the treated, that difference now taking conditional on subjects being in the designated treatment condition. So again, for time today, I'm not going to go into all the details of the different interpretations of these various estimands, but maybe just one takeaway is that note that in this framework, there's not one notion of what a causal effect is, right? There can be many different notions with different interpretations defined for different subpopulations. Now, to try to get back from these potential outcomes to actual observed data, you would make a consistency assumption which says that the observed outcome for an individual should equal their potential outcome corresponding to that observed level of the treatment. And this consistency assumption is maybe starting to hint at some of the challenges we're going to face when we try to estimate these potential outcomes and their means and associated causal effects from actual real-world observed data. And that's because when working with observational or non-randomized data, it's very likely that the treatment and the outcome share some common causes. And these so-called confounding variables are going to introduce these potential sources of bias that if we don't adjust for them when trying to estimate the potential outcome means from the observed data is going to result in, well, biased estimates. So when it comes to trying to estimate for confounding variables when analyzing observational data, there are many different approaches you can take. Propensity score-based methods like matching or inverse probability weighting would use a model for the treatment as the basis to adjust for confounding. But for the purpose of this demo, we'll be interested in estimation by regression adjustment, where we'll be using a model for the outcome variable. So a kind of quick note on some terminology here. The steps which we'll discuss on this slide in a little bit that we perform when doing estimation by regression adjustment, they line up pretty much exactly with the steps you perform when computing predictive margins. The difference is that the language associated with predictive margins doesn't necessarily make these same causal assumptions. So in that sense, they're a bit more general. So in many of our modeling procedures, like we'll see in PROC BART, they use a syntax that reflects that more general setting of a margin type terminology. And in some more explicitly causal procedures, where we're assuming you're making those causal assumptions, you'll see a slightly different language used, like potential outcome means, as we discussed on the previous slide. Again, no, roughly the same steps, just the difference in what type of assumptions you're making. And moving forward in this demo, we'll just assume all the causal assumptions hold. So in that case, how do you perform this type of analysis? Well, you would begin by fitting a model for your outcome variable that involves the treatment you want to study and the confounders you want to adjust for. From that fitted model, you would predict these counterfactual outcomes for each level of the treatment which you're interested in studying. And then by averaging these predictions across all of your data, you can end up with an estimate for the potential outcome mean, so long as these causal assumptions of identifiability and ignorability hold. Now, when performing an analysis using this type of approach, there are many critiques that get raised, typically associated with model misspecification. So that is on top of making the causal assumptions that I'm adjusting for the correct set of confounders X, I still have to assume that the model I'm fitting for my outcome, given those confounders in the treatment, is correctly specified. And this can, of course, be very challenging when working with observational data where we don't control the data generating process, or we maybe don't have a lot of information about the data generating process and a lot of insight into it. On top of that, extrapolation is fundamentally part of this type of analysis, right? I'm predicting these counterfactual outcomes for unobserved levels of treatment, so I'm performing some extrapolation. And then on top of that, right, many of the model diagnostics that we would like to use to assess our model's predictive performance, well, they're based on residuals, and I can't compute residuals for counterfactual outcomes, right? So those are the critiques you see associated with this type of analysis. And when we think about those critiques and compare them to the properties of BART models we discussed earlier, we can start to see this kind of like almost perfect alignment where the sky's open and we see this, again, just great ability of BART models to assess some of those, address some of those challenges. And this gives us some idea of why in many kind of causal inference data competitions and bake-offs, BART-based approaches tend to perform very well and are typically one of the top performing methods. So that would be the flexibility of BART models and the fact that they're non-parametric. That helps us mitigate concerns about model misspecification. Again, I don't have to pre-specify any type of interactions or nonlinear relationships. The algorithm can learn them. Also, the good performance of the default BART model without any need for hyperparameter tuning and its good generalization, well, that can limit some of those concerns about extrapolation. And then finally, again, when performing causal inference, we're probably interested in uncertainty quantification. And in that case, it's really nice that we can naturally do that with these BART models through that Bayesian approach. So again, we get this really beautiful alignment between properties of BART models and issues that we'd like to address when performing a regression-based approach to causal inference. So that's all of our background material. Let's now start to look at some examples of how you can perform these types of analyses using the BART procedure. The data that we'll be analyzing here is the smoking weight data set, where we will be interested in this type of causal question of what effect does quitting smoking have on individuals' change in weight over a 10-year period. So our initial population here are all individuals who reported being smokers in the baseline year. I'm not going to go into too much detail about the other variables in our data here. For more information about this data set, you could look at the documentation for the causal treat, CA effect, or BART procedures in SAS, where we use these data in all those cases. Also the book What If by Miguel Hernan and James Robbins. But we'll just assume the additional confounders that we're adjusting for are going to satisfy all those causal assumptions. So a few things to highlight about this code, one of which is, again, how easy it is to specify these BART models. Right? I'm just using the traditional SAS modeling syntax here to specify my outcome, the predictors, which of those are categorical, and I don't have to think about all of those hyperparameters in the background that guide the BART prior and the sampling process. I can just rely on the good performance of the defaults. The second thing that I would like to highlight is how to perform our type of causal analysis and try to estimate those potential outcome means. Here I'm going to be using these margin statements, again reflecting that kind of more general predictive margin terminology, where in each margin statement I am specifying one predictive margin that I would like to estimate. So I'm giving it a label and then specifying the variables that will define that predictive margin and the values that they should be set to during those computations. So here I'm defining two, one for if everyone were to quit smoking and one if they were to not. And then I'm also using this margin diff statement to request the difference between these two quantities. And here we can see those results as part of the output. And again, making those causal assumptions, these would correspond to estimates for potential outcome means, and their difference would correspond to an estimate for the ATE, the average effect of quitting smoking on weight change in this entire population, about 3.2 kilograms. One other little note about syntax here is note that, as we see here for PROC BART, each margin statement defines one predictive margin to estimate, and that is for computational reasons, because again, it can be very time-consuming to score data using these BART models. And that's going to be a little bit different than if you were to use the margin statement in some of our linear modeling procedures like PROC GenMod or PROC Limix, where in those cases, its syntax is more like the LS mean statement, where you specify a variable and then you get the predictive margins for all of its levels. For computational reasons here, we're just doing that slightly different for PROC BART. Final bit of syntax, which I want to cover, is how I am saving my fitted model in an analytics store by using this store statement. And that is because, as we see here, in addition to using PROC BART to fit a model and compute predictive margins relative to the covariate distribution in my training data, I can also use this procedure to take those previously saved models and now score new data or compute predictive margins relative to some other covariate distribution. So as we see here, no model statement. I'm just specifying that previously saved model using the restore equals option. I'm requesting the same predictive margin computations, but now the data which these are being computed relative to are my input data, where I'm using this where clause to restrict things to only those individuals who actually quit smoking. So in this case, with the causal assumptions applied, my predictive margins estimates are like estimates for those potential outcome means conditioned on subjects being in the treatment condition, and their difference would now be an estimate for the ATT, that other causal estimand. So maybe a quick note about how the difference is about the same, 3.2 versus 3.1 kilograms, but the predictive margins themselves have both decreased by about 1 kilogram, reflecting the differences in these different populations. Now, something that I should also mention is that if you're not interested in taking this purely Bayesian approach to uncertainty quantification using BART models, you can probably greatly reduce the number of samples of the ensemble that you're using or that you're saving if you only want to use these models for predictive purposes, right? And you don't need all those samples for that uncertainty quantification through that Bayesian approach. So I want to demonstrate that here, where in this case I'll be interested in using these BART models as input to estimating potential outcome means and an ATE through targeted maximum likelihood estimation, or TMLE. So this is a so-called doubly robust approach to estimating causal effects, and it involves modeling of both the treatment and the outcome. In this case, I can do so fitting both of those models with PROC-BART, since PROC-BART can be used to analyze data with continuous or binary response variables. So I'm using this NMC option to now only save 200 samples of the ensemble. So there's probably some small impact on predictive performance, but a great speed up in terms of how long it takes to train the model and score data with it. And I'm saving this much smaller model for the outcome, and then I'm also fitting my model for the treatment. And I'm creating an output data set based on those results that has the predicted probability of being in what I'll call the control condition for this analysis. And here in this little bit of data step code, I get the predicted treatment probability for my treatment level. And here I'm using PROC-CA effect to take those predicted outcome values and perform estimation by TMLE. Of course, for time today, I can't go into the details of the CA effect procedure syntax, but maybe just know PROC-CA effect is a model agnostic tool for estimating potential outcome means and causal effects by various methods. What do I mean by model agnostic? I mean PROC-CA effect doesn't fit any models itself, right? It's just going to operate on pre-computed values you provide as input to the procedure, like how I'm doing in these POM statements with this treat prob equals option. I'm specifying the variable in the input data set that contains the predicted probability of being in that treatment level, as specified by the treat lev equals option. And for TMLE, I'll also need some predicted counterfactual outcomes. I could provide those as input as a variable in the data set. But in this case, I'm using this outcome model statement to have PROC-CA effect compute those for me, where I'm specifying that saved model. And here we can see the result is, again, about a 3.2 kilogram estimate for the ATE, pretty similar to what we saw using PROC-BART earlier in that kind of purely Bayesian regression-based approach. So to summarize, BART models are this very flexible and easy to use predictive modeling technique that have been observed to be one of the top performing methods in a lot of causal inference data competitions, in part because a lot of those competitions use data set sizes that are amenable to the application of PROC-BART. We're not looking at huge data sets in those cases. You can perform these types of analyses by using the BART procedure. And if you're not interested in using it in this kind of Bayesian perspective, you can always, again, reduce the number of samples of the ensemble that you're saving, probably at some hopefully small cost on predictive performance, but a great computational speed up. So for example, if you use the BART node in SAS Model Studio, where prediction is only of interest, it uses a very different set of defaults than the procedure, and it is going to save for you that much smaller number of samples. So I think I maybe have time for one question, but if you don't get a question in now, know that I will be at the STAT booth in the Innovation Hub for pretty much the remainder of the conference whenever the Innovation Hub is open. So you can always come by and ask me any questions about PROC-BART or SAS's offerings and statistics in general. Thank you very much.
Let's give it all up for Michael Lamb. Thank you so much, Mike. Today we'll be doing questions in a first come, first served basis. Raise your hand if you have any questions and I'll bring the mic over to you and you can ask away.
Maybe
Anybody?
If someone's thinking of questions, something I'll just say as a background, I probably should also say is, for those of you who didn't attend Shilong's talk right before me, know that the area of causal inference is a big area of development for us. So in addition to what I covered today, talking about PROC-BART and CA effect, there are many other tools in SAS-STAT and econometrics, the causal tree, PS match, causal med, causal discovery, deep causal, deep price procedures. So a very big area beyond just what I could cover in today's talk.
All right, thank you so much, Michael.
Thank you, everyone. Enjoy.
Everyone give it up for Michael Lamb one more time.